Hello everybody, welcome to 2021 paper 1 of Edexcel's A Level maths course exam paper. So this was set in 2021 October. This would have been a COVID paper, so it would have been scheduled for the summer of 2021 but then was postponed. I'm since coming to the realisation that it's probably more efficient and slicker and looks better and is explained clearer when I type out my solutions rather than writing them out in my pen, so it takes longer to record. But let me know in the feedback comments if you find this more helpful or useful. I'm suspecting it is. It just takes a bit longer to record, but it's worth it if the benefit's there for the students. So do let me know if you have any strong thoughts one way or the other about handwritten solutions or me just typing them out and then revealing the text. Anyway, let's have a look first of all together at the solutions step by step. First of all, of course, starting with question number 1. So question 1, we have f of x equals ax cubed plus 10x squared minus 3x minus 4. And we're told that given that x minus 1 is a factor of f of x, find the value of the constant a. You must make your method clear. This is, without saying it, an application of your knowledge of the factor theorem. What it's saying here is that you need to know if x minus 1 is a factor, then x being positive 1 is therefore a root of the equation. So our starting point is to look at this constant a and then deduce that since x minus 1 is a factor of f of x, like I've said, x equals 1 is a root of x. So we can now use this fact to work out the value of this underlying constant a. So if I sub in x being equal to 1, that'll give a value of 0. So when x equals 1, I'll have the following. F of 1 will be 0. So this bit here is set to be 0. Then I'll have 0 equals a times 1 cubed plus 10 times 1 squared, because, again, that's what we're setting x to be. Then minus 3 times a times 1 minus 4. This, of course, will neaten up quite a lot. We get 0 equals a plus 10 minus 3a minus 4. This simplifies to 6 minus 2a. So 0 equals 6 minus 2a. That can only be true if a equals 3. And so here we have it, a equals 3. That's question 1 done, so we're off the mark and can now have a look at question 2. Question 2, we have a quadratic equation. Given that f of x equals x squared minus 4x plus 5, where x is any real number, express f of x in the form x plus a all squared plus b, where a and b are integers to be found. This is just asking us to complete the square, essentially. So what we do for part A is we take the x squared. There's no coefficient in front here, so that's good. We can go on and just do it. So we just put an x in the bracket. The coefficient of the x, minus 4, we half that. So half of minus 4 goes to minus 2. We close brackets and square. We always then minus off this value here squared. So this symbol is always a minus. Minus 2 times minus 2 is positive 4. So we minus off the 4. And then, of course, add the 5. We now simplify this down as our final step. So we get x minus 2 all squared, and minus 4 plus 5 overall, of course, just gives us plus 1. We're now going to use this to help us with part B. I'll just call this f of x, in fact, because it is f of x. So for part B, write down the coordinates of P, where P is the y-axis, where it meets the y-axis. So it meets the y-axis when x is equal to 0. So when x is equal to 0, we're going to have nothing minus nothing plus 5. So the coordinates of P are simply going to be 0 and 5. You just sub in when x is equal to 0. The minimum point at point Q, this is the turning point. Now, to find the turning point when you've already completed the square, the turning point essentially is given by these two numbers. So the turning point of Q is this value here with its sign switched. So the minus 2 becomes plus 2, that's the x-coordinate of the maximum. And the y-coordinate of the maximum, or minimum I should say, of the turning point, is just this number here without its sign changed. So it just stays at being positive 1. So those are our answers for B part 1. And B part 2. Now, if you have a particular model of ClassWiz, which I'll show you here, there is another way the calculator can actually show you what this is, essentially, without you having to remember that. So it's a bit of a sort of hacky way of doing it, but, you know, as long as it helps. So what we can do here on a decent enough calculator. This is just one of many. This is my favourite. On the class whiz here, you go to Menu, then press Option A to scroll to Equations. Press Equals. We obviously have a polynomial. It was a quadratic. Press 2. And so press 2 because the highest power of the quadratic is power 2. We had 1x squared, so type in 1. X was minus 4. Then type in 5 and press Equals. This now gives you the solutions. These are imaginary, so unless you're doing further maths, this might not mean too much. But never mind. If you keep pressing Equals, you get to the minimum value of y. The minimum value, the turning point of this function, is when x is 2, look, and y is 1. So what I'm trying to tell you here is, in a sense, a good calculator will tell you the coordinates of a turning point is 2 and 1. So if nothing else, that's a good double check. Maybe a great one. In fact, if a question doesn't say that, doesn't stop you from using a calculator to just get the solution. Question 3 is about sequences. So this here, we have a sequence U1, U2, U3, and this is a term-to-term rule. We've defined the next term based on the previous term. So UN plus 1 is k minus 24 divided by the previous term value. We're starting off with U subscript 1 being equal to 2. K is an integer, and we're told that U1 plus 2 lots of U2 plus U3 equals 0. We need to show this to be true. So let's start off by considering. First of all, U1 I'm going to have in red, U2 in blue, U3 in green. So we're told U1 is equal to 2. So from this, we can work out what U2 is. But let's just state, again, that U1 equals 2. Because we know it, just write it down again clearly. So therefore, U2 will be k minus 24 divided by the previous value U1. So U2 is going to be k minus 24 divided by 2. Well, 24 divided by 2 is 12, so U2 must be k minus 12. In the same way, U3 will be k minus 24 divided by this k minus 12. So this is an expression for U3. I'm going to leave this like it is for now. I'm now going to return to this expression here, this equation rather. We can now use this to then work out, well, to show that 3k squared minus 58k plus 240 equals 0. So this is U3. I'm not changing this. So now using the fact that U1 plus 2U2 plus U3 equals 0, we can put this into an equation. So U1, of course, is just 2. So we're going to get 2 plus 2 lots of U2, so 2 lots of k minus 12. That was U2 from here. And then plus U3, which is this thing here, equals 0. So what I'm going to suggest to do now is expand these brackets and just neat it up slightly. So if I expand the brackets out, I'm going to get this as our next step. Expand out, I get 2k, plus that k gives 3k. 2 times minus 12 is minus 24. Minus 24 plus 2 gives minus 22. Then this awkward fraction at the end equals 0. If I now multiply through by this denominator, I will then make this into a quadratic, which is what my target actually is. So if I multiply both sides by k minus 12, I get this as my next result. So now I'm going to need to expand out 3k minus 22 with k minus 12. So if I highlight this in yellow and expand out, I'd get this result. Then, of course, a minus 24 at the end equaling 0. Then the final step, 264 minus 24 will simplify to 240, which gives us our actual solution as required. So therefore, simplifying one more step, we arrive at our result, which is what we wanted to prove, so we've nailed part A. Part B, we're now going to use part A to find that value of k, giving a reason for our answer. So we now know, for part B, well, we've shown that 3k squared minus 58k plus 240 equals 0. We can now use a quadratic formula to solve this. So again, if you want to use a calculator, you can do. So this time, if I go into Menu, Option A for Equation / Function, Polynomial, degree 2 because it's quadratic. It says x here, x, k, whatever, same difference. The coefficient of the squared term is 3. Minus 58k is the k coefficient, then 240 is the last one. Press equals. My first solution is 40 over 3. My second solution is 6. So therefore, using the quadratic formula, my answers are k is equal to 6 or 40 over 3. The question though doesn't say find the values of k plural, it says find the value singular. So one of these must not be valid. So what did the question tell us about what k had to be? Well, if you look here, k must be an integer. An integer essentially just means it has to be a whole number, which can be negative, but can't be a fraction. So in other words, 40 over 3 is not an integer, so we need to reject this option here. So we reject 40 over 3 and go for the integer option k equals 6. So therefore, for b, k must equal 6. Finally, for part C, find the value of u subscript 3. This is actually much easier now. Now we know what k is, and we had an expression for u subscript 3 from part A. We can just sub in k is 6 into that to work out what u subscript 3 is. So u subscript 3, just reminding you again, was this here. It was k minus 24 all over k minus 12. If I sub in now that k is 6, this now becomes 6 minus 24 all over 6 minus 12. 6 minus 12 is minus 6, so this fraction will simplify to 24 over minus 6, but because I'm minusing this fraction, minus 24 over minus 6 is the same as minus 4. So u subscript 3 is 6 minus minus 4, which of course is the same as 6 plus 4, which is 10. So therefore, the third term, u subscript 3, must equal 10. Question 4, we have a curve with equation y equals f of x, where f of x is given by x squared plus the natural log of all of 2x squared minus 4x plus 5. And this has a single turning point where x is equal to alpha. Show that alpha is a solution of this equation below. Well, what does it mean if we have a single turning point, or a turning point at all? So turning points will happen when the derivative function is equal to 0. So the first thing to mention here, I would say, would be there's a turning point when f dashed of x is equal to 0. So what we need to do here is we need to differentiate f of x. So f of x obviously comes in two pieces. There's an x squared piece and an ln piece. So x squared, well obviously that's easy to differentiate, that just goes to 2x. Now differentiating the natural log of a function. The natural log of a function, if you differentiate it, we need to know the standard result. It becomes a fraction. It goes to the denominator being the original function and the numerator being the derivative of the function you just were trying to find the derivative of. So for this one, the denominator would be 2x squared minus 4x plus 5, and the numerator would be the derivative of 2x squared minus 4x plus 5. So what we'd have is this. The derivative of 2x squared minus 4x plus 5 is 4x minus 4. So that's where we get this on the top. And of course, like I said, derivative of x squared is just 2x. So we want this to be equal to 0. This is a fraction, this isn't. So I'm going to suggest we get the 2x to become a fraction by multiplying and dividing by 2x squared minus 4x plus 5 to give us something that looks a bit like this. So I'm not changing the value of 2x, I'm just rewriting it like this, so I can then convert it into something that looks like a fraction to get a single common denominator. So I do have now a common denominator, so now I can expand the top and simplify. So if I put this all over 2x squared minus 4x plus 5, I get this as the next line. This expands to give 4x cubed minus 8x squared plus 10x, when of course I've got 4x minus 4, all over 2x squared minus 4x plus 5, and that equals 0. So this is the gradient function. I want this to be equal to 0. This is going to be equal to 0 when the numerator of it is equal to 0. This denominator is never going to be equal to 0. So what we're wanting here is to realise that actually this whole thing is going to be equal to 0. The turning point will be when this thing here is equal to 0. So what we're going to do now, we're going to set this equal to 0. And so now what we need to realise is this whole thing, because it's going to be equal to 0, we set 4x cubed minus 8x squared plus 14x, because we've got 10 plus 4x there, minus 4 equals 0. So this equation when we solve it, will tell us, therefore, where the turning point is, and because the turning point is at alpha, this therefore is a solution, an equation to find a solution for alpha. We're not quite what we need to be at there. What we need here are these coefficients to be halved. So the final step, if we now divide everything by 2, we therefore get 2x cubed minus 4x squared plus 7x minus 2 equals 0, which was the equation we wanted to arrive at and show was the case in the first place. So we've done part A. For part B, we have an iterative formula. X subscript n plus 1 is 1/7, 2 plus 4x subscript n squared minus 2 lots of x subscript n all cubed. And that could be used to find an approximation for alpha. We're going to start with x1 being 0.3, and what we're going to do is calculate, given each answer to 4 decimal places, first of all the value of x2. So all we're doing here is just plugging in x being 0.3 in place of these 2 values here. So to find x2, we just simply do this calculation here. So if we do this one together, so we can show that it works. Whoops, that's not what I intended to do. So back at menu, normal mode. So I've got 1/7, so type it in exactly as it looks on the exam paper. Then 2 plus 4, and I'll put the inputs in brackets. That's all squared. And then I've got minus 2 lots of the input, 0.3. All of that to the power cubed. Close brackets. I get this awkward fraction here, so press SROD. I get about 0.32942857 and so on. But I want these answers to 4 decimal places, so I round this off, and my final answer for B part 1 is 0.3294. For part 2, I now need to find x subscript 4. So I need to find x subscript 3, and then use that value of 3 to find the next one, x subscript 4. So I'm going to show you the slow way of doing this, then I'll show you the much faster way. So to find x subscript 3 first, we're going to use this value, x subscript 2. So x subscript 3, doing it the slow standard way, we input x subscript 2 now, so we do the same thing again, and then we generate our answer for x subscript 3, which should be an awkward number. Again, you might want to round that if you really wanted to. I'd suggest actually not, because this is only an interim step. X subscript 3 doesn't really mean anything to us. We're only interested in x subscript 4. So here, actually, I would keep it as a unrounded, uncurtailed decimal if you're going to use this method. I'd advise you use a method I'm going to explain in just a moment, in fact. But anyway, now we have x subscript 3. We can plug this back in into the equation to find x subscript 4. The equation for x subscript 4 is as follows, using the 0.3375 and so on from before. We get an answer like this, which again we then need to round to 4 decimal places to get 0.3398. Now, the method I'm suggesting and strongly urging you use is this one. Go back to the calculator. This is what we had for x subscript 2. So what we can do now, because x subscript 2 is stored in our calculator's memory, rather than typing in what x subscript 2 is manually, we can just toggle back and type in, press ANS. And that will make our calculator use its memory to type in what x subscript 2 was in exact form. So press equals again. Look, it gives us x subscript 3 instantaneously. And the best thing now, we can just press equals now to get x4, x5, and so on and so on. So just one more press of an equals. Look, we get 0.3398, which was indeed x subscript 4. So this is a really powerful tool. There's lots to know on a good calculator, so know it as well as you possibly can to save yourself as much time and to get as many marks as possible in your exams. Anyway, now finally, part C. Use a suitable interval and a suitable function that should be stated to show that alpha is 0.341 to 3 decimal places. Now, strange as it sounds, my suggestion here is to actually return back to GCSE thinking and consider again error intervals. So something's been rounded to 0.341 to 3 decimal places. So consider that for a moment. First of all, I need to give a function that should be stated. So we're trying to find alpha, so let's use this function from part A, because this was a function which we have proven will find alpha. So call this not f of x, because we always use f, so call this maybe g. So alpha is a root of this equation. So I'm going to mention this in a moment. Yeah, alpha is a root of this equation, because it says so in part A. Now, returning to what I said about error intervals and bounds, if something's been rounded to 3 decimal places and it's ended up being 0.341, then obviously it must have been closer to 0.341 than it was to 0.340 or to 0.342. So just as a moment, I'm going to imagine this as a diagram, like so. So if it's been rounded, alpha, it's closer to here than these two, then it must be, if I imagine halfway lines in between here and here, and there, like so, and I highlight 0.341, then alpha must have been in between these limits here. It must have been closer than halfway in between 341 and 340, and obviously must be closer to 341 than to 342. And so what we need to do here is find these midpoints in between 340 and 341, and the midpoint in between 0.341 and 0.342, which of course are 0.3405 and 0.3415. So if we can now test g of x at these two crucial points, and we get a change of sign, that will prove that alpha must be in between these two values. And if alpha is in between these two values, then literally if it's in between them, somewhere in this gap, then it must have rounded to 0.341 to 3 decimal places. So that's the explanation. Now let's actually apply it. So what's g of 0.3405? Well, g of 0.3405, if you try this on your calculator, it's a bit of a long-winded thing to type in, but just take your care with it, take your time. You should get minus 0.00131. Importantly, that's a negative value. So I'm just going to put there, that's minus value. Now if we try g of 0.3415, we've come out with something which is just slightly positive, 0.00366. That's a positive value. Now I apologise, I'd probably tell my students off for doing this if they did this themselves. I've run out of space, so I'm going to put my conclusion at the top rather than the bottom, so you can just see it on the one screen. We've done the hard work now we just need to conclude. So all we've shown now is that because g of 0.3405 has a negative value and g of 0.3415 has a positive value, that's shown that there must be a solution to this equation in between 0.3405 and 0.3415 because there's been a change of sign. So the solution is in between these two values, but we have been told from part A that that solution is alpha. So we just need to conclude with a fairly brief sentence without going overboard, something like this. So since there's a change of sign from g of the first one to g of the second one, and you need to say g as a continuous function, then alpha must have indeed rounded to 0.341 to 3 decimal places. Question 5. Read this carefully at the top. You need to show all stages of working. You can't just rely on the calculator to do all the work for you here. So it's about showing carefully all stages of working. So it's the examiner's made this explicit, so take this as a warning. So a company are making a profit of £20,000 in its first year of trading. So that's year 1. A model for future trading predicts that the yearly profit will increase by 8% each and every year. That's quite optimistic, but you know, maybe. So that the yearly profits will form a geometric sequence. So geometric is when each value is a previous one multiplied by a certain constant. Arithmetic is when you're adding the same thing. Geometric, so you're multiplying by the same thing. So according to the model, for part A, we need to show that the profit in year 3 will be 23,328. So just picking this information out slightly, its profit is going to increase by 8% each and every year. So if you think about GCSE again and decimal multipliers, what would you need to multiply by to generate an increase of 8%? Well, the decimal multiplier to do that would, of course, be multiplying by 1.08. So, essentially, what's happening to find the profit for any 1 year, we're going to be timesing 20,000 by 1.08 a certain number of times. So the profit for any particular year is going to be 20,000 multiplied by 1.08 to the power n, or so you might think. Just be very careful here. Think about what the profit was for year 1. The profit for year 1 was £20,000. So I don't times £20,000 by 1.08. So for year 1, I need to be multiplying this by the power 0. So this n here actually needs to become an n minus 1. So really important here, that needs to be 1.08 to the power n minus 1. So don't forget that n minus 1. Next, we can now just input n is 3 to work out the profit for year 3. So for year 3, profit for year 3 is going to be 20,000 multiplied by 1.08 to the power 3 minus 1, which of course is just 1.08 squared. If you try that, you should get 23,328 as required. Part B, find the first year when the yearly profit will exceed £65,000. So we're wanting this expression here to be greater than £65,000. So we're trying to solve an equation where the unknown is in the power. So at some stage we're going to be using logarithms here. I'm going to try and get this 1.08 to the power n minus 1 on its own. So my first step, I'm going to suggest we divide by 20,000 on both sides. If we do that, we'll now see that 1.08 to the power n minus 1 must be greater than 3.25. If I now take logs, natural log to be honest, of both sides, I'll now be able to bring this power to the front. So the next step, I'll now have n minus 1 at the front multiplied by ln of 1.08 must be greater than ln of 3.25. And now I want to have this n minus 1 on its own, so I'm going to divide both sides by ln of 1.08. So if I divide everything by ln of 1.08, I get n minus 1 must be ln of 3.25 divided by ln of 1.08. So let's just try and see what that is actually. So ln 3.25 divide by ln of 1.08, that gives 15.314 and so on and so on. But that's what n minus 1 is. So I need to add 1 to both sides to get what n is on its own. So n must be 16.31. In other words, we need a bit more than 16 years for the profit to exceed £65,000. First year, we want an integer value for our answer, so we can't leave it at 16.31. And a common mistake would be to round down, because this is closer to 16 than it is to 17. But you need to think of it like this. N needs to be in excess of 16 years, which is to say that 16 years would not quite be enough to exceed £65,000. Therefore, the first whole number year where this is exceeded must be when n is 17. So the final answer is when n is 17 years. And to be honest with you, if you're a bit confused about the rounding up or rounding down idea, if you find this a bit sort of ambiguous, try it on your calculator the really simplistic way. Type this in with n being 16 and 17. So if n were 16, for example, then the formula was n minus 1. So 16 minus 1. If I were to try this, look, I don't get £65,000, not quite anyway. But if I were to try n being 17, that now does exceed £65,000. So that's another way you can double check your answer. And I do stress double check rather than just do on your calculator, because the question does say show all method stages on your working. Now part C, we need to find the total profit for the first 20 years of trading and giving our answer to the nearest £1,000. I'm going to expand this space. I've got a bit more room to work out part C. So part C, we need to sum all these profits. This formula here is to find the profit for just each individual year. To find a profit sum, there is actually a formula to sum a geometric series. So this has been taken from the formula book, The formula to find a total profit, or a total something for a geometric series, is this. The sum of the first n terms is a brackets 1 minus r subscript, to power n, all over 1 minus r. So we've got 20 different terms to add together because we've got 20 different years of profit. So let's just consider this in a bit more depth. The formula we had for just 1 year, the profit for any 1 year is 20,000 multiplied by 1.08 to power n minus 1. So our common ratio is 1.08 each and every time. A is our first term. The first term would be the profit in year 1, which was £20,000, and n, we said, was 20. And if this here confuses the idea that you're summing all these different profits, maybe write down profit for year 1, profit for year 2 to get a feel of what you're adding together. So the actual sum we're performing is this one here. 20,000 plus 21,600 plus profit in the third year plus etc, etc, all the way to the profit in the final 20th year. So imagining it like this might make it easier to picture what's going on. This is just optional. Essentially what we do need to know is that A is 20,000, R is 1.08, and there's 20 terms. So these are the values we're going to plug in to this formula to find the profit total in the first 20 years. So the profit for the first 20 years is 20,000 brackets 1 minus 1.08 to the power 20 all over 1 minus 1.08. So if we try this now and see what we get, 20,000 brackets 1 minus 1.08 to the power 20 all over 1 minus 1.08. Press equals, we get 915,239.28 and so on and so on. That's a very large profit. However, our answer needs to be to the nearest £1,000, so this then becomes £915,000. Question 6 returns to vectors. So I have a triangle here. So from A to B, we can represent this with a vector minus 3i minus 4j minus 5k. And from B to C, we can use I plus j plus 4k. The vector A to C is geometrically illustrated by the line AC. So using the information we have here, can we find a vector going from A to C? So let's label on what we have so far. So we've got from A to B, which goes from A over to B like this way. So that's minus 3i minus 4j minus 5k. From B to C goes here, along the top from B to C. So if I want from A to C, I'm going to do this in a green line going from A all the way up to C. Now to go from A to C, I'd have to go from A to B and then from B to C. So A to C is AB plus BC. That's the first step. So AB, in terms of vectors, we just write out in terms of vector in IJK notation, and same for vector B and C. So this is what we have, and then we just simplify as we would do any normal algebra. So minus 3i plus 1i gives minus 2i, minus 4j plus 1j gives minus 3j, and minus 5k plus 4k gives minus k. And so A to C is minus 2i minus 3j minus k. For part B, we need to show that cos of ABC equals 9/10. So what we need to do here, we need to go from the vector arithmetic to actually thinking what the actual magnitudes, the actual sizes of the sides of these lines on the triangle would be. So to find the magnitude of a vector, what we need to do is to square root the sum of the squares of all its components. So first of all, for A to B, squaring all its components, minus 3 squared, minus 4 squared, minus 5 squared, add them all together and square root. It's a similar idea for Pythagoras. To find the length of hypotenuse, we square the other two sides, add, then square root. Here we've just got 3 things to square, add, then square root rather than 2. From B to C, that's going to be the square root of 1 squared plus 1 squared plus 4 squared. And over here for a to c, what we're going to have for a to c is the square root of minus 2 all squared plus minus 3 all squared plus minus 1 all squared. And if I fill in what these actually are, maybe start off away here, this actually becomes the following in terms of sizes of the sides. That simplifies to root 50, from b to c simplifies to root 18, and a to c simplifies to root 14. We now need to think about the actual cosine rule. This is a non-right angled triangle. It mentions cosine. So ABC is the angle at B, which is this one in yellow here. So I'm trying to find cos of this angle is exactly 9/10. So the cosine rule is as follows. Now, to find angle A or side A, always label either the side or angle in question as either little a if it's a side or big A if it's an angle. So because we're interested in cos ABC, even though this is the angle at B, I'm going to call this big A, and therefore the side opposite to it I'm going to call little a. So little a and big A, respectively, are root 14 and the angle ABC. So if I label these on like so, and then B and C in any order are going to be the other two sides. So B and C in any order are going to be root 50 and root 18. So if we now plug these values in to this formula, we now arrive at this. Root 14 all squared equals root 50 all squared plus root 18 all squared, a squared equals b squared plus c squared, minus 2 times b times c times cos a. This can now be simplified quite a lot. So root 14 all squared is obviously just going to be 14. Root 50 times root 50 is 50. Root 18 times root 18 gives 18. Now these surds here have simplified. So root 50 is the same as root 25 times root 2. And root 18 is the same as root 9 times root 2. But by simplifying them like so, what I'm going to get here is a root 2 times another root 2. And root 2 times root 2 just becomes 2. So this will help us to simplify further. So the next step of simplification, we have 14 equals 68. 50 plus 18 gives 68. That 2 stays as it is. Root 2 times root 2, replace with that 2. Root 25 is of course 5, and that root 9 becomes 3. So how many lots of cos A here in the coefficient? Well, 2 times 2 is 4, times 5 is 20, times 3 is 60. So I've actually got 14 equals 68 minus 60 cosine A. So if I add 60 cosine A to both sides and then subtract 14, I can see that 60 cosine of A must be 54. If I now divide both sides by 60, I can see that cosine of A must be 54 over 60, which of course simplifies down to 9/10. Therefore, cos of A, which are the same as cos of A, B, and C, of course, is 9/10. Question 7 is about circle geometry. We've got a circle, capital C, with equation x squared plus y squared minus 10x plus 4y plus 11 equals 0. Part A, we need to find the coordinates of the centre of C. To find either the centre or the radius, what I'd suggest we do is we complete the square on the x parts and the y parts separately. So looking at this equation here, I've got x squared and minus 10x. So complete the square on this bit, I get x minus 5 all squared, half of minus 10 becomes minus 5, square it, and then minus off this thing squared. I've also got y squared and a plus 4y. If I complete the square on these bits, I'm going to get y plus 2 all squared, because half of 4 is 2, so y plus 2 in brackets all squared, then minus off this 2 here squared, which gives me that minus 4. Then just remember I've got plus 11 equals 0, so add this on. Next step is to simplify. Minus 25 minus 4 is minus 29, plus 11 overall, that's minus 18. So the next step, I've got x minus 5 all squared, plus y plus 2 all squared, minus 18 equals 0. Now, I've done enough to find the coordinates of the centre, but I may as well just get it into the form where I've got one bracket squared plus another bracket squared equals a number. So if I just add 18 to both sides now, I've got x minus 5 all squared plus y plus 2 all squared equals 18. I want to carry on to get this number on its own, because this number on its own has a certain significance. I've got an equation of a circle, and we can get the x into brackets squared and the y into brackets squared. This number on its own will always be equal to the square of the radius. So these numbers here, the -5 and the +2, they tell us essentially what the coordinates of the centre of a circle are. We take these values and switch the signs. So switch -5 becomes +5, 2 becomes -2. So the centre of circle C is just these values here with the signs switched. As I say here, the significance of that 18 on its own, that's the radius squared. And that's going to help us for part 2. So what's the exact radius of C, giving it as a simplified surd? So I know that r squared must equal 18. That's not fully simplified, because actually I could just use my calculator here, I suppose, for this one. If I just type in root 18, it'll do it for me. 3 root 2. The reason why is because 18 is the same as 9 times 2, so I can split root 18 into root 9 root 2. But root 9 becomes 3, hence I've got 3 root 2. Part B, I would suggest, to be honest, to sketch this out on a diagram. I've got a line L with equation y equals 3x plus k, where k is some constant. L is a tangent to the circle C. Find the possible values of k, giving your answers as simplified surds. Well, this equation here has got a gradient of 3 quite clearly, so it's going to be going upwards, this straight line. I now know this circle C, though, has got a centre at 5 and -2. So I'm going to sketch it on here. That's my circle, 5 -2, that little dot here. I don't know if you can see it, that's the centre. And now if I imagine this line here being a tangent to this circle, it could go in one of two places. It could either be along the top like this. Don't worry about these intercepts. You're not expected to know through a sketch what these are, but just sketch them on anyway. Essentially, you can hopefully see here, there's going to be two different y-axis intercepts, which will correspond to the two possibilities for what k is. So I'm going to call one of these here, oops, that's a mistake, I'm going to call one of these here k1 and the other one k2. So next step, what we can consider next, is the equation of the circle itself. We had x squared plus y squared minus 10x plus 4y plus 11 equals 0. But y, if I just highlight now in green, we're told what y is in terms of x. So if I now substitute in what y is, 3x plus k, in terms of the letter y instead, I'll now end up with this result here. Just replacing y with what y is in terms of x. Y is 3x plus k. So obviously this looks an absolute and utter mess. The key thing I'm looking at here is if L is a tangent, but if I solve this and use the idea of a discriminant, but I'm going to mention this in a second. Right now I've got some expanding and simplifying to do. So if I expand out these brackets here and then simplify it eventually, I'll get x squared plus this bracket here goes to 9x squared plus 6kx plus k squared. Expand this, I get 12x plus 4k, then plus 11 equals 0. So now let's try and simplify this all down. So I've got how many x squareds? Well, I've got x squared plus 9x squared, so I should have 10x squared to finish off with, in purple as you can see. In the pink, how many x's I've got? So I'm going to have 2 x's here, plus 6 kx's. So I've got 2x plus 6 kx. And finally, the constant terms on their own is a constant k squared, 4k, and 11. So grouping them together like so, I get this. And I've factorized out the coefficients of the x like so. So in terms of the quadratic formula, the coefficient of x squared, the a, is 10, b is 6k plus 2, and c, the constant term, even though it looks awkward, the constant term is k squared plus 4k plus 11. I'm now going to return to this idea of L being a tangent to C. If L is a tangent to C, that means it's got exactly one solution. It just scrapes at one point, not 2 points, and does actually hit once, but it means that each time we've got a solution, there's only exactly one solution. We need to remember what this means about a discriminant. If a quadratic only has one solution, its discriminant must be equal to 0. And discriminant is b squared minus 4ac. We set that equal to 0. And so in our case, b squared is 6k plus 2 all squared. So filling in this information here for our equation of a circle, we get this next. B squared minus 4 times A times C equals 0. So let's expand out 6k plus 2 all squared. That'll give us 36k squared plus 24k plus 4. And then expanding all this here, it's minus all this times by 40 essentially. I'm going to get minus 40k squared. Minus 40 times 4, minus 160k, minus 440 equals 0. If I now simplify this down, so 36k minus 40k squared, I'm going to have minus 4k squared, for example. In the other ways, I'm going to get minus 136k, because it's 24k minus 160. And then the number on its own is minus 436, because it's minus 440 plus 4. I can now solve this using the quadratic formula on the calculator, but essentially, if you solve this, you'll get two different values for k, which will correspond to k subscript 1 and k subscript 2. So the final step, using the quadratic formula solver, you should find that either k is minus 17 plus 6 root 5, or that k equals minus 17 minus 6 root 5. Question 8. A scientist is studying the growth of two different populations of bacteria. The number of bacteria, capital N, in the first population is modelled by this equation here. N equals AE to the power KT, where T is defined as being non-negative. A and K are positive constants, and T is the time in hours from the start of the study. So we're given some information here which we can now use to do part A, which is finding a complete equation for the model. So essentially we've got this general model here. To find a specific equation, we need to find the values of N, A, and, sorry, the value of A and K. N is obviously the variable. So let's have a look at the information we're told. We're told, first of all, that there's 1,000 bacteria in the population at the start of the study. At the start of the study, that's when T is equal to 0. So what this is telling us is that when T equals 0, the starting number of bacteria is 1,000. So therefore, A equals 1,000. If you were to plug in T being equal to 0 into this formula, you get 1,000 equals A times E to the power K times 0. E to the power of K times 0 is E to the power 0, it's just 1. So that would just reduce to 1,000 equals A. The next piece of information is that it took exactly 5 hours from the start of the study for the population to double. Well, if the start population was 1,000, if it doubles, that means it then becomes 2,000. So what this is saying here is it took 5 hours for it to increase to 2,000. So when T equals 5, N equals 2,000 for this one. So 2,000 equals A, which we've reduced now as 1,000, multiplied by E to some constant K, multiplied by T, which is time. So T is 5, because we've got here 5 hours. We can now actually work out what K is from this. So from this equation, if we divide both sides of it by 1,000, what we'll now get is that 2 equals E to the power 5k. If we now get that 5k to the front by taking logs on both sides, we'll now get that ln of 2 equals 5k. To isolate k on its own, I can now divide everything by 5, so therefore, dividing by 5, I see that k must be 1/5 of ln2. So I've worked out that A is 1,000 and that k is 1/5 ln2, so I now have my complete model for this equation. So finally for part A, the complete model is therefore that n equals 1,000 e to the power 1/5 ln2 multiplied by t. For part B, I need to find the rate of increase in the number of bacteria in this population exactly 8 hours from the start of the study. Give your answer to two different figures. Rate of increase, essentially I need to find dn by dt. As awkward as this looks, all you need to consider is this 1/5 ln2 is just some constant. If I'm differentiating e to the power of some constant times t, the power is locked but when I'm differentiating, the constant term comes to the front. That's all I need to remember. So from that, dn by dt is 1,000. That 1/5 ln2 comes to the front and multiplies with 1,000, and e stays to the same power, because the power is still locked. So this simplifies now, because 1/5 times 1,000 is 200. So this becomes 200 ln2 multiplied by e to the 1/5 ln2 times t. So now I've got the general equation for the rate of change of the number of bacteria for any time. So now I can input t being equal to 8 to find the rate of change, dn over dt, for when t is equal to 8. Well, when t equals 8, what I've done now, I thought, well, 1/5 times 8 is 1/5 of 8, which becomes 1.6. And so what this is going to give me now is 200 ln2, and that becomes e to the power 1.6 ln2, because 1.5 times 8 gives 1.6. So if we now try this on the calculator, so 200 ln2, then that to the power, so e to the power of 1.6 ln2. We get 420.24 and so on and so on. But we want this answer to be given to two significant figures. So actually we're just going to round it to 420 I mean to say. Finally, for part C, there's another model we're going to introduce now. So the number of bacteria M in the second population is modelled by this equation here. And importantly, K has the same value found in part A. So K, which appears here, has the same value of what's found in part A. Well, K was 1/5 ln2. So if I take this and multiply it by 1.4, 1 over 5 is 0.2. 0.2 times 1.4, that becomes 0.28. And so essentially, 1.4K, this is going to become 0.28 ln2. So I'm just going to rewrite this in a slightly easier way. Essentially, m equals 500 e to the power 0.28 of ln2 multiplied by t. Anyhow, so I've got two different models for populations, capital N and capital M. After capital T hours, after the start of the study, the number of bacteria in these two different populations is the same. So what we can do here is we can set this one equal to that one for some time, capital T, which we can then solve. So this is our first setup of how to solve this question. So set one equal to the other for some capital T we need to find. So first of all, what we can do to get this neatened up, we could maybe divide by 500 on each side. If I divide by 500, and I get 2e to the power 0.2 ln2t equals e to the power 0.28 ln2 multiplied by big T. What we can now do to get these powers to the front is to take natural logs of both sides. So if I take logs of both sides now, I get ln of all of this equals ln of all of that. Now first of all, this is the natural log of a product of two things. This is ln of 2 multiplied by e to some power. If I'm taking the log of a product, I can split the log of a product into two separate logs. This is what I'm going to do here. I'm going to split this one into ln2 plus ln e to the 0.2 ln2t. So I get this next line. So now what I can do with the ln of e to the power of parts here, what I can do here is I can actually now just bring the powers to the front, because obviously natural log undoes the fact we're doing e to the power of something. So the next step now is to say I've got ln2 plus 0.2 ln2 multiplied by t equals 0.28 ln2 multiplied by t. There's a few ways of solving it from here, but what I'd suggest to notice, if you can, is we've got ln2 as a common factor of all of these terms. So I can divide through everything by ln2. So if I divide everything here by ln2, I'll now get 1 plus 0.2t equals 0.28t. I can now subtract 0.2t from both sides, to get that 1 must equal 0.08t. Then finally, dividing everything by 0.08, t will be 1 divided by 0.08, which is 15, and the units are hours. So the final answer for part C, t would be 15 hours when the two populations are equal to one another. Question 9, we've got f of x expressed in this fairly awkward looking algebraic fraction. F of x is 50x squared plus 38x plus 9 all over 5x plus 2 all squared multiplied by 1 minus 2x. X is defined as not being equal to minus 2/5 and not equal to a half, so that this denominator never becomes equal to 0. We're also nicely told that f of x can be expressed like this, in other words in terms of partial fractions. So for A part 1, we need to find the value of b and c. So because f of x equals this and equals that, I can say this bit here equals the partial fraction part like so. And this is the way into solving this question. So I'm going to set up this to equal that as my first step. Now, I'm going to multiply through both bits of this by the whole of this denominator. So I multiply through everything by 5x plus 2 squared and multiply by 1 minus 2x. I now arrive at the following result. This, I just got left with a numerator. So I get 50x squared plus 38x plus 9. One lot of the 5x plus 2's cancel, but I've not got another lot of 5x plus 2 times 1 minus 2x. Multiplying this fraction by all of this, the 5x plus 2 squared cancels, leaving me with just 1 minus 2x. And finally this fraction, if I multiply by all of this denominator, the 1 minus 2x will cancel, just leaving me with c multiplied by 5x plus 2 all squared. The next thing we need to do is to pick different values for x so that some of these brackets disappear so we can work out the others. I'm trying to find b and c essentially. So what I'm going to pick to do first is to let x equal a half. If I let x equal a half, then the a bit will disappear and the b bit, because this 1 minus 2x bracket becomes 0. So that now allows me to focus on working out what this c is equal to. So if I sub a half into both sides, I now arrive at this. 50 lots of a half squared plus 38 times a half plus 9 must equal c times by 9 over 2 all squared, because that becomes a half times 5, 2.5 plus 2, which is 4.5, which is a fraction, is 9 over 2. If we now simplify this on the calculator, we now get that 81 over 2 equals 81 over 4 times c. Therefore, dividing everything by 81 over 4, we should see that c has to equal 2. Next, I could do with working out the b bracket. So I don't want to have anything to do with a or c now. So what value of x here would make the c bracket and the a bracket disappear? Well, if I want the c bracket to be non-existent, I want 5x plus 2 to be equal to 0. If 5x plus 2 equals 0, 5x equals minus 2, therefore I could set x equal to minus 2/5. So for the next bit, if I set x equal to negative 2/5, the a bracket and the c brackets will disappear entirely, leaving me with just this. 50 lots of minus 2/5 all squared plus 38 times minus 2/5 plus 9 will equal b multiplied by 1 minus 2 times minus 2/5. So that's the same as 1 plus 4/5, which is 1 4/5, which is 9/5. This is where the 9/5 comes from. Again, being careful on your calculator to get this neatened up slightly, you should see that you have 9/5 on the left and 9/5 b on the right. So 9/5 equals 9/5 times what? Of course, b has to be equal to 1. So therefore, b equals 1. Now for part 2, we need to show that the a equals 0. Now there's a few different ways of doing it. I would suggest just to try letting x being equal to 0. So for part 2, if I just let x equal 0 and sub that in, this bit here becomes nothing plus nothing, just becomes 9. And because I know what a is, so I know what b and c is, if I just sub in 0, this bracket just becomes 2 and that 1. So get a times 2 times 1. B, we worked out, was 1. when x is 0, that bracket just becomes just 1. So that becomes b times 1, like so. Then finally, the c bracket, if x is 0, just becomes 2. So it's c times 2 squared. So then if I neaten this up, it's fairly obvious what's going to happen. I've got 9. That's a mistake. That's really annoying. That should say 2a. My bad. So that should say 2a. Whoops. Plus 9, because 2 times 1 is, of course, 2. So therefore, if 9 equals 2a plus 9, then obviously a has got to be equal to 0. So now we can just conclude and say that a has got to be equal to 0 then. So now we've got what f of x is. Now we've worked out a, b, and c. We can now use binomial expansions to show that in ascending powers of x, ascending means powers of x getting bigger, f of x is in this form, where p, q, and r are simplified fractions to be found. So we need to go up to the terms in x squared. So let's just remind ourselves what we have so far. We've got f of x equals a is 0, so this just vanishes altogether, equals b, which is 1 over 5x plus 2 all squared, plus c, which is 2 all over 1 minus 2x. So rewriting this in terms of in power notation, this becomes 5x plus 2 to the power minus 2 plus 2 lots of 1 minus 2x all to the power minus 1. In a moment, we need to recall the general binomial expansion formula, which is here, which I've taken from the formula book. Now, if you have a look how it's defined, we're best putting the variable last, so I'm going to put the 5x last in a moment, and the first term needs to be equal to a 1. This term is a 2, so what I need to do here is to factorise out the 2, so it's 1 plus 5x all over 2. So the first bracket, if I rewrite it like this, all still in big brackets, all to the power minus 2, then I can now apply this power minus 2 to the 2 and to the bracket. So this becomes 2 to the power minus 2, which is a quarter, and this bracket all to the power minus 2 still. So I now get this. So now what I can do is I can apply this binomial expansion on the blue expansion and then the red one separately, and then combine afterwards. So just for the blue, make a bit more space, I'll have a quarter, and then the first term will be 1, look, and then plus n times x, so the power multiplied by that variable. So it's going to be minus 2 times 5x over 2, which is what I've got here, and then plus the power multiplied by the power minus 1, so minus 2 times minus 3, all over 1 times 2, which is the same as 2 factorial, multiplied by that second term all squared, which is 5x plus 5x all over 2 squared in my case. I put a plus and dot 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 because this expansion would go on forever. But of course, we're going to simplify this ever so slightly in a moment. The other bracket, this one, I've now got 2 lots of this. So the next one, the red, we can have 2 lots of the first term 1, and then the power times minus 2x, so minus 1 times minus 2x, like so. That'll give me a plus 2x. And then the power times 1 less the power, all over 2 factorial multiplied by minus 2x all squared, plus blah blah blah, because of course it would carry on into x cubed, x to the power 4, and so on. So what I'm going to do now, I'm just going to approximate this. So I'm going to curtail it, I'm going to cut it off after the x squared terms. So I'm going to say this is approximately equal to, and then I'm just going to stop it after the terms we see. So I've just neatened this up slightly. So 1 stays as 1, minus 2 times 5x over 2 becomes minus 5x. And this here, the 2's cancel on the top and the bottom. Over here, 5 squared is 25, times 3 is 75, and 2 squared is 4. So it becomes 75 all over 4x squared. For red, stopping after the x squared terms, becomes 2 lots of 1, then minus 1 times minus 2x is plus 2x, and this bit simplifies to plus 4x squared. If I now expand this out, so multiply all this by a quarter, and double everything in this red bracket, and I get this. A quarter minus 5 quarters x plus 75/16 x squared plus 2 plus 4x plus 8x squared. I can now combine these into this form here. So the constant term p will just be a quarter plus 2, which will be 9 quarters. The x squared term, I've got 4x minus 5 quarters, which will leave me with 11 quarters of an x. And the x squared term, 75/16 plus 8, overall is the same as 203/16. So that's the fully simplified version of f of x up to at least the x squared term. For part 2, we need to find the range of values of x for which this expansion is valid. Well, it says here, if we've got this expansion, the second term needs to have magnitude less than 1. And so what we're saying here is this thing has to have magnitude less than 1, and this thing here must have magnitude less than 1. So f of x is valid when 5x over 2 is less than 1, the size of it, and when minus 2x is less than 1. So if I now rearrange this to get x on its own, essentially just multiplying by 2 and dividing by 5 for the first one, and this one if I just essentially divide by 2, I can then deduce that f of x is valid for when mod x is less than 2/5 and mod x is less than 1/2. But if mod x needs to be less than 1/2 and less than 2/5, that's only true when x is less than 2/5. So the inequality which satisfies both of these is that x must be less than 2/5. So therefore, that's our final solution to find the range of values for which this expansion is valid. X is simply less than 2/5. Question 10 involves trig identities. So it says here to show all stages of your working, solutions relying entirely on calculator technology are not acceptable. So we need to be very clear where we're getting our answers and methods from. So first of all, part A is proving this identity here. So given that 1 plus cos 2 theta plus sine 2 theta is not going to equal 0, prove that this identity holds and that the left-hand side is equivalent to tan theta. So if you notice here, we have double angles, coses of 2 theta and sines of 2 theta, but we need to prove this is identical to tan of a single theta. So we need to be thinking about using the double angle formulas to break these down in from 2 thetas into single angles. So obviously the cos 2 theta and the sine 2 theta are what we need to focus on. So I'm going to highlight these. And the double angle formulas that relate to cos and sine of 2 theta are as follows. So for sine 2 theta, it's more obvious just to go for, obviously, the only one there is. Cos 2 theta has different variations. So in terms of which one to pick, it's just a case of just try one out. So what I'm going to go for here is I'm going to substitute cos 2 theta with 2 cos squared theta minus 1. And I'm going to sub sine 2 theta for 2 sine theta cos theta. So the first step is to change the left-hand side from looking like this to looking like this, just replacing cos 2 thetas with 2 cos squared thetas minus 1 and sine 2 thetas with 2 sine theta cos theta. If we now have a look to see if this fraction will simplify, well, it will. So the numerator of this one, we're going to get 1 minus minus 1, so we're going to get 2 minus 2 cos squared theta. And the denominator here, we're going to get 1 minus a positive 1, so we're just going to left with 2 cos squared theta at the bottom. So the top and the bottom will look almost identical, but on the top I'll have a 2, then minus 2 cos squared theta, and on the bottom I'll just start with 2 cos squared theta, and we'll have 2 sine theta cos theta on top and bottom as well. So simplifying, the next step will end up with this. And now if we look at the top, 2 minus 2 cos squared theta. Well, 2 minus 2 cos squared theta, I can factorize into 2 lots of 1 minus cos squared theta, like this, because I've just changed 2 minus 2 cos squared theta to become 2 brackets 1 minus cos squared theta. Just factorize out of 2, like so. But by doing this, though, I can now think that, well, 1 minus cos squared, that's going to become sine squared. So if I replace 1 minus cos squared with sine squared, I now get this. So now on the top, I've got 2 sine squared theta plus 2 sine cos. On the bottom, 2 cos squared theta plus 2 sine cos. So to end up with tan, obviously I want a lot of factorising and cancelling to happen. So the clue here is obviously to try and factorise this if possible. And of course I can. So on the top, I can factorise out a 2 sine theta. And on the bottom, I can factorise out a 2 cosine theta. So if I do this and factorise, and I get this next step, so because in the brackets I've got sine theta plus cos theta in the numerator and denominator, I can cancel these brackets on the top and the bottom, and as well because I have a factor of 2 on the top and on the bottom, I can also cancel out this 2. So cancelling out the 2 and the brackets, like so, will just leave me with sine theta over cos theta, and sine theta over cos theta, of course, is identical to tan theta. I should apologise, these here should be identity symbols rather than equals. I couldn't quite find the formatting to make that work, but strictly speaking, be using identity symbols, these ones here, rather than equals when we're talking about identities. Part B, it says hence, so we're going to use part A. So use part A to solve for the interval from 0 to 180 this trig equation here. So if we now compare this here to what we have on the left-hand side, which I'm going to code in blue, it's almost one and the same thing. Only thing here is the variable theta has been replaced with x, and every instance of the variable here, we've got double the coefficient over here. So essentially, theta has been replaced with 2x. And so if this identity goes towards tan of theta, then if I double the angle and call it x's instead of thetas, this must be the same as tan of 2x. So therefore what we're solving here is tan of 2x being the same as 3 sine 2x. I next need to remember that tan is of course a composite. Tan is sine divided by cos. So if I just rewrite tan of 2x as sine 2x over cos 2x in a moment, and bear in mind as well, because I'm talking now in terms of 2x's, I can now double these limits. So if my solution range needs to go from 0 to 180, then in terms of 2x, for 2x, I can have it in between a range of 0 and 360 exclusive. So as I'm saying, just rewriting tan in terms of sines and coses, I get this step. Sine 2x all over cos 2x equals 3 sine 2x. If I now multiply through by cos of 2x, I arrive at sine 2x equals 3 sine x. So 3 sine 2x cos 2x. I can now subtract sine 2x from both sides on the journey towards factorising. So if I now subtract sine 2x from both sides, I'll now see that 3 sine 2x cos 2x minus sine 2x equals 0. Both of these groups now have a factor of sine 2x in them, so if I factorise out the sine of 2x, I get the following. I get that sine 2x, brackets, 3 cosine 2x minus 1 must equal 0. So therefore, either one of two things. Either we've got that sine of 2x is equal to 0, or what's in the brackets is equal to 0. Now, if in the brackets is equal to 0, I'm solving 3 cos 2x minus 1 equals 0, which rearranged with cos 2x being the subject, I'd be wanting to solve for when cos of 2x equals 1/3. To solve when sine of 2x equals 0, that's a bit more obvious. So 1 is the sine graph rooted on the x-axis. So sine of 0 is 0, sine of 180, and sine of 360. So 0, 180, 360, and all multiples of 180. The only one of those multiples of 180 which is in this range is 180 itself. Okay, because 0 isn't allowed. I need to be bigger than 0, but less than 360. So 2x could be equal to 180. Cos of 2x equaling this is not so obvious. So let's find the principal angle by doing shift cos. Let's do arc cos. So shift cos of 1/3. That tells us the principal value for cos of 2x, for 2x is 70.53 degrees. So if I just use a cast diagram now to help me slightly with cos of 2x, then if I want it to be between 0 and 360, I could have it even the A quadrant, which would be 70.53 degrees, or it could be down in the C quadrant, where cos of 2x is also positive. This angle here would be 360 minus 70.53. So if I do that now, 360 minus 70.53, I get the other angle must be about 289.47. So therefore, I've worked out my three different values for what 2x can be. So 2x could either be 180 degrees, where sine 2x would be equal to 0, or from cos of 2x equaling 1/3, I can have either 70.53 degrees, this one here, or going all the way around to this one in the C quadrant, 289.47 degrees. However, I'm wanting to solve this in terms of x only and to one decimal place. So next I need to divide everything by 2 to arrive at this. Therefore x equals either 90 degrees, 35.3 degrees, or 144.7 degrees. Question 11 is about areas underneath curves. So figure 2 shows a sketch of part of a curve with equation y equals ln x all squared, where x is greater than 0. Now this finite region R, which is bounded in between the curve, the x-axis, and the lines x equals 2 and x equals 4. And this table's got corresponding values of x and y, with values of y given to 4 decimal places. We're told explicitly we need to use the trapezium rule with all the values of y in the table to obtain an estimate for the area of R, giving an answer correct to 3 significant figures. So the trapezium rule. This is in the formula book, and I'm just going to post it here, just so you know what it is. So this means to get an approximation for the integral in between the limits of x being a and b, we can basically use this approximation here, where h is the difference between b and a divided by the number of strips we're using. So to work out what h is, I sometimes think it's easier to actually just sketch in on a graph just to see what h actually is. So if I just highlight h in red, these figures in the table for x, obviously x needs to go from 2 to 4, which were labelled, but adding on 2.5, 3 and 3.5, we can see here we're going to be talking in terms of 1, 2, 3, 4 different strips. So we're dividing a gap of 2, because from 4 to 2 is a gap of 2. 4 minus 2 is 2. Dividing that by n, being 4, because there's 4 different strips, our h in this case is going to be 0.5, which you can see quite obviously the gaps as we're going up are in increments of 0.5. So h is 0.5. y0 and yn, they just mean the first y value and the last y value respectively in the table. So y0 in our case is going to be 0.4805, and yn will be the last value of y, which is 1.9218. y1, y2, all the way up to the penultimate y are just all the values in the middle. So these ones here just correspond to these 3 values for y in the middle of our table. All that's left to do now is to infill this data into this formula. And so the integral is going to be approximately equal to half of h, so half of 0.5, which is 0.25, multiplied by the first y value plus the last y value plus 2 lots of all the other y values in between. So that's the calculation we're having to do. So type it in carefully on your calculator. You should get a value of 2.408525, and then answering the question as it's been asked, giving our answer to 3 significant figures, that'll then become 2.41. For part B, we need to actually find the area using exact algebraic integration. So what we need to do is to use algebraic integration to show that the exact area of R can be given in this form, where a, b and c are integers, whole numbers essentially, to be found. So I'm integrating a product, but this isn't one where it's a reverse chain rule job. So if it's not reverse chain rule or not a substitution, it's going to be integration by parts. And the method I'm going to use here, unashamedly, despite some people thinking, what is he talking about? It's going to be called the DI method. I'll put a link on the video description and on the video itself, because I've basically just borrowed this. I've stolen it, essentially, from a different YouTuber. I think it's a really good and easy method. Once you try it a few times, this is. I'll explain as I go how to do this. So, I'm integrating y, which is ln x multiplied by ln x. What I first need to do is to construct a DI table with alternating pluses and minuses down the side, as many rows as we need. So in the D column, we put the function which we can differentiate, and in the I column, we put the function we wish to integrate. Because this is ln x multiplied by ln x, we don't have any choice. In one column, we're going to have to put ln x. In the I column, we're going to put another ln x. Now, can we differentiate ln x? Yes, we can. That goes to 1 over x. I'm going to assume here that you may have forgotten the standard result of how to integrate ln x. So assuming you forgot this, just put a question mark here for the time being. I'll show you how to find the integral of ln x from first principles, again, ironically, using integration by parts. So if I want to find what the integral of ln x is, I need to consider it as the integral of 1 multiplied by ln x. So consider it like this, and I can use this DI method again. So in the D column, I put whatever comes first in the acronym LATE, where L stands for logs, A is algebraic, T is trigonometric, E is exponential. So L for logs comes first. 1 is algebraic. Consider it as being x to the power 0. So in the D column, I'm going to put ln x. In the I column, I'm going to put 1. So differentiate ln x gives me 1 over x. Integrating 1 gives me x. I stop differentiating and integrating down these rows when I find a row which, if I take the product of the two things, if I can integrate that product, I stop, and that's my final row. So if I take the product of 1 over x and x, multiply these together, I get 1. Can I integrate 1? Yes, I can. So this is my final row, so I can stop. So I underline my final row, and I take the product of the diagonal of all the other rows above until I get to a point where I'm touching the final row. So that's just one diagonal I do. So I'm going to do ln x multiplied by x, then I'm going to take minus 1 over x times x and find the integral of that. So it's minus the integral of 1 over x times x with respect to x. So the diagonal product minus the integral of 1 dx, because 1 over x times x simplifies to 1. Now if I integrate 1, of course I get x. So this becomes x ln x minus x. I'm going to put in brackets the constant of integration, because when we use this DI method, we don't need to worry about the constant of integration until after, and that's only if we've got a definite integral to consider, which we have here. So essentially, if you integrate ln x, then the standard result, we get x ln x minus x. So I'm going to replace this question mark with what it is now. We've got x ln x minus x. Over here now, we can now use this DI table to actually integrate ln x squared. We just need to check if we can integrate the product of this final row. So 1 over x multiplied by all of this would simplify to ln x minus 1. Well, I've integrated ln x, which is this line itself, and we can integrate minus 1. Minus 1 we just integrate to minus x. So this is the final row we need. So I'm going to underline this row and take the diagonal product of the rows above it. So what I'm going to do here is underline that final row and take the diagonal product. So therefore the integral of ln x all squared from 4 to 2 is the diagonal product, which is ln x multiplied by x ln x minus x in between the limits of 4 and 2. Then because there's a minus sign here, it's minus the integral of this product. So 1 over x times x ln x, that just simplifies to ln x, and then 1 over x times minus x gives minus 1. But it's minus that because of this minus sign here. So now we can actually fill in these values. So next, and there's quite a bit to explain in this next couple of steps. But first of all, this in red, inputting the higher limit of 4 gives me ln4 for ln4 minus 4, then minus the lower limit, just input when x is 2, gives me ln2 to ln2 minus 2. And integrating this in the blue, it's minus the integral, of course. Ln x integrates to x ln x minus x, but minus 1 integrates to another minus x. So I've got x ln x minus another x, hence x ln x minus 2x, in between the limits of 4 and 2. Now, as you can see here, my target is to get it in terms of natural log of 2, not in terms of natural log of 4. So we need to think that the natural log of 4 is the same as ln of 2 squared, because 2 squared is 4. So ln4 is the same as ln of 2 squared, which is the same as 2 lots of ln2. So I'm going to replace all instances of ln4 with 2 lots of ln2. So ln4 becomes 2 ln2. 4 lots of ln4 becomes 4 lots of 2 ln2, which is a ln2. Over here I've got minus ln2 times by 2 ln2, which is minus 2 times ln2 all squared. Then minus ln2 times another minus. Minus times a minus makes a plus, so I get positive 2 ln2. It's crucial of these to be really careful with the signs and the working throughout. Now this last one, because we've now integrated it, we can input the limits on this one as well. So if we input the high limit when x is 4, x ln x minus 2x becomes 4 ln4 minus 8. Then we minus off when we input for the lower limit. When we input 2, x ln x minus 2x becomes 2 ln2 minus 4. So that's what we minus off on this side. We can now simplify again, as long as we're careful and take our time. So now, this bit here, 2 times 8 is 16, ln2 times ln2 is ln2 squared. 2 ln2 times minus 4 gives minus 8 ln2. That term leave as it is, that term leave as it is. Again, before I said ln4 is the same as 2 lots of ln2. So this is the same as 4 lots of 2 lots of ln2, which becomes 8 ln2 minus 8. And then the same way here, that's already in terms of ln2s, so that's absolutely fine. So now we can simplify again. So let's think about simplifying the red first. So if we simplify the red, I've got 16 ln2 squareds minus 2 ln2 squareds. I'm going to get 14 ln2 squared. And then 2 ln2 minus 8 ln2 is going to be minus 6 ln2. So the red goes to this, and the blue simplifies to this, which I'll explain. 8 ln2 minus 2 ln2 gives me the 6 ln2. Then minus 8 minus a minus 4 is the same as minus 8 plus 4, which takes me to minus 4. But again, because what I'm doing here is subtracting all of this blue anyway, that minus a minus 4 will become a plus 4 anyhow. So piecing it all together now, I'm going to have 14 lots of ln2 all squared. Minus 6 ln2 minus another 6 ln2 is minus 12 ln2. And minus 4 is plus 4. So that's my final answer given as shown. Not that it asks us to do this, but A is 14, B is negative 12, and C is 4. Question 12 is some applied pure. So it's still pure maths, but it's related a bit to mechanics here. So we've got the graph of the trajectory of a golf ball after the ball has been hit until it first hits the ground. The vertical height, h meters, of the ball above the ground has been plotted against the horizontal distance travelled x meters, measured from where the ball was hit. The ball's model is a particle travelling in a vertical plane above horizontal ground. Given that the ball is hit from the top of a platform of vertical height 3 meters above the ground, as shown, reaches its maximum vertical height after travelling a horizontal distance of 90 meters, not yet shown, and is a vertical height of 27 meters above ground after travelling a horizontal distance of 120 meters, again not shown here as such. We need to now find h in terms of x, given that h, the height of this golf ball, can be modelled as a quadratic function in terms of x. So it doesn't say exactly how to express this quadratic function. It could be expanded, it could be in factorized form, it could even be in the form of completed square form. And that is actually the form I'm going to go for here. So these questions, you ask different teachers, you might get different answers, all valid, for how you could express this quadratic model. But I'm going to go here for completed square form. I'll explain why in just a moment. Essentially, it's for this reason here. It's reaching its maximum vertical height after travelling a horizontal distance of 90 meters. So if I just highlight this turning point in blue on the diagram, then the turning point, essentially, we're told what the turning point is when we have a quadratic given to us in completed square form. So because this is a key piece of information, I'm thinking, well, we may as well give this quadratic model in a completed square form. We may as well add on some more information about this model as well. So it's at a vertical height of 27 meters after travelling 120 meters horizontally. So if I add in another point here, 120 and a height of 27, then in completed square form, it's going to look something like this. The height is going to be some multiplicative constant at the front, x minus some constant here, all squared, plus or minus some other number here. So a, b, and c are just integers we need to find. So this part here, the turning point, when we have this a completed square equation, the turning point is always at b and c. So essentially, the x-coordinate at the turning point is always this value here, what b is, made minus. So what I'm trying to say here is, because x is 90 at the turning point, our value of b is therefore going to be 90. So in the brackets we have x minus 90. So the height is a brackets x minus 90, because b must be 90, and c, because this value here, c, is at the turning point, then that will always relate to the maximum height. Before moving on, also let's not forget we've been told that it starts off from a height of 3 meters. So when x is 0, it's at a height of 3 meters. So you can actually deduce using simultaneous equations what we need from the graph. So using the fact when it's 120 in the horizontal direction, we're 27 high, we can substitute this into our model for h. So h, 27, equals a, and substitute in that x is 120, b, we've reduced is 90, all squared, plus c. So this can actually be simplified. So 120 minus 90 is 30, and 30 all squared is 900. So I can rewrite this more simply as 27 equals 900a plus c. If I now substitute in that when x is 0, h is 3, and I get this equation, and I get that 3 equals a, brackets, 0 minus 90 all squared plus c. 0 minus 90 is minus 90, minus 90 multiplied by itself is 8,100. So put more simply, this equation can be written like this. I've now got a pair of simultaneous equations to solve. I can now do one equation, subtract the other, or I could use my calculator to do this for me, either or, doesn't particularly matter. So if I do this equation, subtract the other, I now see that 24 must equal minus 7,200a. If I now divide both sides of this by negative 7,200, I can now see that a must be minus 1 over 300. Taking this value of a and substituting it back into one of these equations here, I'm going to pick the top one because the numbers are smaller, in my opinion makes it easier. Then I'll now have that 27 equals 900 multiplied by negative 1 over 300 plus whatever c is. Well, 900 multiplied by minus 1 over 300, that's just simply negative 3. So I've got 27 equals negative 3 plus c. If I now add 3 to both sides, I can now see that c must be 30. So now actually I've got a complete model. I've worked out that a is minus 1 over 300, b in completed square form is the x-coordinate at the maximum, which we were told is 90, and c we've just worked out is 30. So plugging a, b and c into this expression here, our fully completed model to finish off part A is this. h equals negative 1 over 300 brackets x minus 90 all squared plus 30. Now for part B, we're asked to find the maximum vertical height of this ball above the ground. Well, one of the beauties about having the equation in completed square form is essentially we've got our answer already. The maximum vertical height of a ball above the ground is just simply 30 metres. Part 2 is slightly trickier. It says now to find the horizontal distance travelled by the ball from when it's first hit to when it was first hits the ground, giving your answer to the nearest metre. Well, it'll first hit the ground when h is 0. So that's what we're going to do. We're just going to substitute in that h equals 0. We can then solve from there. So I'm now going to say that 0 equals minus 1 over 300 x minus 90 all squared plus 30. If I now subtract 30 from both sides, then I get that negative 30 equals minus 1 over 300 times x minus 90 all squared. If I now multiply both sides by negative 300 now, I now get that 900, because 300 multiplied by another 30, sorry, 9,000 I mean to say. 9,000 must equal x minus 90 all squared. If I now square root both sides, of course considering plus or minus, so square root 9,000 gives 94.868. That'll be accurate enough. 94.868. So obviously the negative option will give me something like negative 4.8 meters. And that would relate to this point here. Imagine it going back in time, which in our particular case is a nonsense. So we're going to reject that negative one. So essentially we're just looking at the positive root. So therefore x is going to be 94.868 plus 90, and that's going to give a value of, I do believe, 185 meters to the nearest meter. But let's just add on 90 if ever you're not sure. Yes, 185, and again it says giving your answer to the nearest meter. That's why I'm giving it rounded like that. Finally now, for part C, the possible effects of wind or air resistance are two limitations of a model. Fair enough. Give one other limitation of the model. So let's keep it simple. So mention any one of the following things. The ground is unlikely to be perfectly horizontal. That's my favourite. That is the simplest, I think, way of getting the extra mark. The ground is never going to be perfectly horizontal. You could also say, if you wanted to, the ball is obviously not actually a particle, so the model does not consider the ball's size. So in terms of when it lands, that's going to be off by at least a few centimetres, for example. The ball's trajectory is unlikely to be entirely in a 2D plane. It's not going to go straight up and straight down. There'll be spin or rotation. Obviously, you can't say it's going to be blown off course because you're in danger of duplicating what the examiner's already said not to mention again. So don't say about air resistance or wind. Mention spin or rotation instead. And a fourth option you could perhaps put is a quadratic model for H may only be an approximation for a different or much more sophisticated function, which is sort of hidden beyond. So actually the quadratic model might not be an actual valid model itself. It may only be an approximation to something a bit more sort of magical going on behind the scenes. Question 13 is about a curve C that has parametric equations x equals t squared plus 5 all over t squared plus 1 and y equals 4t all over t squared plus 1, where t is defined as any real number. We just need to show that all points on C satisfy this relation here. So y is given as it is, so to square y isn't so much an issue. X, though, is given like this, so doing x minus 3 and then squaring will be an issue. So we need to focus in on what x minus 3 is in a simpler form. So x minus 3, if I just write x as a fraction over here first, and then if I write minus 3 like this, just so I'll explain, I can now combine x minus 3 as an algebraic fraction with a common denominator. So I've just rewrote 3 as 3 multiplied by t squared plus 1 divided by t squared plus 1. Obviously, yes, in reality, t squared plus 1 on the top and bottom would cancel, but by writing it like this, just allows me to simplify this into one single fraction. So doing like I'm saying, combining this into one single fraction all over t squared plus 1 would give me t squared plus 5, expanding this out as well, minus 3t squared minus 3 all over t squared plus 1. Overall, the numerator will become 5 minus 3, which is 2, and t squared minus 3t squared will simplify to minus 2t squared. So I'm going to get 2 minus 2t squared all over t squared plus 1. So now I've got what x minus 3 is, and I know what y is. So x minus 3 is that, and y is that. So x minus 3 all squared plus y all squared equaling 4, I can now show this to be true by working out what this is all squared added to this algebraic fraction here all squared. X minus 3 all squared plus y squared equals all this squared plus all of that squared. So it's just now having to have a bit of faith and conviction to back yourself that this will drop out and cancel nicely to just leave us with 4. So common denominator again, which is great, so we can just consider squaring out the tops. So putting all as a single fraction, this one here, the top is going to be 2 minus 2t squared all squared, and this one, 4t all squared. I just did that in one move because it's fairly straightforward. 4 squared is 16, t squared is just, well, t squared. Now if I expand out this first bracket here, I'm going to get 4 minus 8t squared, and then minus 2t squared multiplied by itself will give positive 4t to the power 4. Plus, of course, that's 16t squared. So if I now simplify the numerator, I get 4t to the power 4 plus 8t squared plus 4 all over t squared plus 1 all squared. Now, if you want to, you could maybe do 2 steps here. You could first of all factorize out a 4 of this top line. So it's the same as 4 lots of t to the 4 plus 2t squared plus 1, and then say therefore it's 4 lots of t squared plus 1 all squared. I've just skipped that step and gone straight to saying that this here would factorize into that. As long as you're being very clear and explicit to the examiner that you know this does factorize into that, that's the main thing, to just be absolutely clear that you have essentially told the examiner you know that this factorizes into that. Once you got to this stage, you've essentially cracked it. You've got t squared plus 1 all squared on the top and the bottom, so they'll therefore cancel, and we just have left with a 4, so therefore all this equals 4, which is exactly what we wanted to prove. Question 14. So coming towards the end of the paper now, and for my money this is one of the hardest, if not the hardest question on the paper because of the manipulation involved isn't, in my opinion, very obvious. So we're told we have a function y, which is x minus 4 over 2 plus root x, x being defined as greater than 0. We need to show that dy by dx is 1 over a root x, where a is some constant to be found. So we're trying to differentiate here a quotient, so we need to remember, essentially, ideally, the quotient rule. So if we have y, so if we have y, which equals u over v, then we can say dy by dx is function v multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator, all of that divided by the denominator function squared. So essentially we're applying this here. So we need to differentiate this expression here. And so in our case, our u at the top is x minus 4, therefore u dashed is just going to be 1. V is 2 plus root x, therefore v dashed, if I were to differentiate that, this means x to the half, so the half would come to the front, and then be dividing by the square root of x. So this would give me a half x to the minus a half, which is one of the same as saying it's 1 over 2 root x. So now we can actually evaluate the derivative of this. So dy by dx is going to equal the denominator, 2 plus root x. I'll get a fraction ready here. So I've got 2 plus root x multiplied by u dashed, which is just 1. I'm going to minus from that u, which is x minus 4, multiplied by v dashed, which I'm going to say is 1 over 2 root x. And all that is going to be divided by v squared, which in our case is 2 plus root x all squared. So now what I'm going to suggest we do is we expand the top and just see what happens. So we're going to have on the top 2 plus root x minus x times a half over root x. That's going to become minus a half of x rooted. So it's going to become minus 1/2 of the square root of x. Then finally minus 4 becomes plus 4. Plus 4 multiplied by a half becomes 2. So we have 2 over root x at the end. And all of that is still over 2 plus root x all squared. Now our target is to have it something like this, where we've got something all over root x. And so here, this is the real hard part in my opinion. It's wondering how this will ever simplify. So what I'm going to suggest we do, because obviously we want to end up with a root x, let's try multiplying both numerator and denominator by root x. So this is just a hunch, essentially. This is just something to try and see what happens. Because at least then we'll have the root x involved in the denominator. So if we do this next, what we'll now have is the following. The numerator, when I multiply by this root x on the top, this 2 will just become 2 root x. Root x minus a half of root x would overall be 1/2 root x. So a half root x multiplied by another root x will simply become half x. Then finally, 2 divided by root x multiplied by root x will simplify to just be 2. I'm going to leave the denominator factorized. I'm going to now return to what I think of as being our target, essentially. Our target is this here. So I need to multiply by root x, of course. So my target here, I want to just maybe have some constant on the bottom, and this becomes a 1. So, for example, if I get this to factorize, maybe I could cancel this with the 2 plus root x all squared, because this is a hidden quadratic if you spot it, in terms of root x. We've got root x, and this is root x squared. So what I'm going to suggest we do now to make this more factorizable, to get rid of this factor of a half, we could multiply the numerator by 2. And if we do that to the numerator, of course we'll need to do this to the denominator as well. So we're actually nearly done now, but these steps are not obvious. I think this is a very sort of tricky question. On the top, we're now going to have 4 root x plus x plus 4. And on the bottom, of course, we're going to just get 2 root x, 2 plus root x all squared. Now, if we have a look at the top, the top actually would factorise into 2 plus root x all squared, because 2 squared gives 4. Take the product and double, that's 4 root x, and root x times root x is just the x. So the final step, we may as well show this explicitly, so we're in no doubt of getting full marks. So the top, I'm just going to factorise into 2 plus root x all squared, and the bottom is 2 root x, brackets 2 plus root x, all squared. Final step, now we can cancel this and that, which leaves us with our final answer. We've got 1 over 2 root x. So in other words, this constant a we found to be equal to 2. So we've got 1 over 2x. It doesn't say for us to state explicitly what a is, but of course by writing it as 1 over 2x, it's obvious that we've shown that a equals 2. Question 15, the last question, is a proof question. So we need to prove by exhaustion to show that for n being any natural number where n is 4 or less, that this holds true. N plus 1 cubed is greater than 3 to the power n. So by exhaustion means we need to show it true for every single case. But a natural number means a whole number 1 or greater. So here, for n being 4 or less, we're just simply trying this all the way up from n being 1, 2, 3, and 4. So first of all, let's just try this for when n is equal to 1. So when n equals 1, n plus 1 cubed is just 1 plus 1 cubed, which is 2 cubed, which is 8. And 3 to the power n means 3 to the power 1, which is 3. Clearly 8 is bigger than 3, so we've shown it to be true for n being equal to 1. Next we need to show it true for n being equal to 2. So when n is equal to 2, it becomes 2 plus 1 cubed on the left-hand side, which is 3 cubed, which is 27. And on the right, we've got 3 squared, which is 9. 27, of course, is bigger than 9. So we've shown it's true for n being equal to 2 by just substituting in the values. When n is 3, the same idea. We have this. We get 3 plus 1 all cubed, which is the same as 4 cubed, which is 64. And 3 to the power n becomes 3 cubed, which is 27. 64, of course, is bigger than 27. So shown it's true for n being equal to 3. Finally, you've guessed it, show exactly the same for n being equal to 4. We get this. 4 plus 1 cubed is 5 cubed, which is 125. And 3 to the power n is 3 to the power 4, which is 81. 125 is greater than 81. So shown it's true for n being equal to 4. We then conclude by returning to the original question and show that yes, it is therefore true for all n up to and including 4, where n is a natural number. So finally, just state something like this to conclude. Therefore, yes, n plus 1 all cubed is greater than 3 to the power n, where n is less than or equal to 4, where n is a natural number. Part 2. Given that m cubed plus 5 is odd, we use proof by contradiction to show, using algebra, that m itself is even. So, setting up our contradiction step, we need to assume that there must exist some m somewhere in the universe, such that m cubed plus 5 is odd, and also m itself is odd. So that's our first step. Assume there does exist an m, such that m cubed plus 5 and m itself are both odd. Then m cubed plus 5 we can work out algebraically. But first of all, if m is odd, then how can we express m? Well, an odd number is 1 more or 1 less than an even number. So I can write this odd number as being 2 times some integer plus 1, or 2 times some integer minus 1. Positive numbers are easy to deal with, generally speaking, so I'm going to let m equal 2k plus 1, where k is some natural number. So this is my representative for m. This represents any general odd number. So now m cubed plus 5 becomes 2k plus 1 all cubed plus 5. If we expand this out, I'm going to do 2k plus 1 all squared, then multiply by 2k plus 1 again. So this becomes 2k plus 1, and 2k plus 1 all squared is 4k squared plus 4k plus 1, not forgetting the plus 5 at the end. If I now expand all this out, 2k times 2k squared gives 8k cubed, and I'm also going to get some k squareds from 2k times 4k, which is 8k squared, and then 1 times 4k squared gives 12k squared. But by expanding this out and being careful, you should arrive at this, 8k cubed plus 12k squared plus 6k, and then 1 plus 5, of course, is just 6. Then because all these coefficients are even, we can factorise out a 2 from all of this to arrive at this expression. This is the same as 2 lots of 4k cubed plus 6k squared plus 3k plus 3, which of course is even, because by definition a multiple of 2 is an even number. This is our contradiction. We assumed that m can be odd, and that m cubed plus 5 could be odd too, but we've worked out m cubed plus 5, if m is odd, drops out to be even. This, therefore, is a contradiction. So now we say this contradicts our initial assumption that there can exist an m such that both m and m cubed plus 5 are odd. So therefore, if m cubed plus 5 is odd, then m itself is also odd. So that finishes off question 15 and therefore the whole paper. So thank you for listening. I hope you found some of this useful. Keep revising, keep working hard, keep asking those difficult questions, and you will succeed. So for myself, it's goodbye for now, and I hope to see you soon.